Alright, hi folks, and welcome back to Physics with Captain Rod. I'm making this video to introduce you to the concept of equivalent resistance and to demonstrate how to calculate equivalent resistance. So before we start here, what we got going on. Here I've drawn a very simple circuit over on the left-hand side here. We have a battery. The long post represents the positive terminal, the short post the negative terminal, hooked to two resistors. And this is called a parallel combination. It's parallel because basically the current at this junction has a choice. Some can go through R1, some can go through R2. If I were to go ahead and draw currents in this picture, I'm going to draw a current here. I'm going to call that one I sub B. That's the current basically coming from the battery. I'm going to go ahead and draw a current here. I would call it I1. Current here, I2. And before I move on, it's important to know some things about these currents. This current, the one I call IB, the one coming from the battery, if I were to put an amp meter basically anywhere in green here, all readings would give me current B. That current is exactly the same anywhere in this branch of the circuit. If I were to put an amp meter anywhere in this part of the circuit, I would be measuring I1. And anywhere in this part of the circuit, I would be measuring I2. All right. Now, the idea is I want to be able to given these two resistors, R1 and R2, can I calculate the value of a single resistor that I can put in place of this pair and basically have the battery not know the difference? Have the circuit be the same as far as the battery is concerned. And that would mean that in this picture, whoops, let me do that in black here, the current here would be IB coming out of the battery. And that current in that picture would be good anywhere in that loop. All right, so the $1,000,000 question, how do I find that guy? So, well, here's how. And we're just going to attach the math that we know about these circuits. For starters, we're going to start here, right at that junction, right there. And we think about that green circle that I just drew. Think about the current coming in. The current that I have coming in is this one, the one I called IB. And the current that's coming out of that junction, well, this is coming out of the junction, so is this one. And, basic conservation laws say the charge just can't disappear. So whatever's going into that junction has to be coming out. This is a steady state problem, which means basically this. IB is equal to the sum of these two currents, I1 plus I2. Now, of course, there's no resistance in sight here, is there? Well, remember Ohm's law. We know from Ohm's law that V, voltage, is equal to current times resistance. So current can be expressed as voltage over resistance. So I'm going to go ahead here and talk a little bit about this I1 and this I2, and I'm going to use the picture on the left. And whenever I'm dealing with these pictures, I think it's very handy. I like to color code the potentials. Remember from the IFACS video, important facts about conductors. Conductors themselves are equipotentials. And in this circuit, it's important to note that these are wires, which are made of aluminum, copper, conductors. So I'm going to go ahead and color code this. This is all one potential. From here all the way down to here. Now this would stop at the resistor because the resistor is not a pure conductor. Right? It's stopping there. We are going to have voltage changes across the resistor. Now on the other side of the battery, this is already one color black. I'm just going to leave it, but that's all one potential. And what I want to point out is that whatever the voltage of the battery is, that's the voltage between black and red. And if I come over here, black, red, over here, black, red. So whatever this voltage is, it is the same across the resistor R1 and the resistor R2. So, I should color code the picture on the right. This is all one potential. Right? So keeping in mind that these are all the same voltage, I'm going to go ahead and write each of these three currents as a voltage over a resistance. So, kind of looking at the picture over on the right, I'm going to use the voltage over R equivalent, right? Because the current IB by Ohm's law is this voltage divided by this resistance. Right? I1, I'm going to kind of look at my picture I1, and I'm going to use the voltage across this, which is V, the same voltage, and then over R1. And I2, and I'm going to take a look, I2 is going through this resistor right here. So I'm going to use the voltage across this resistor, which is, again, these are all the same. divided by R2. And because these are the same voltages, they divide out. And we get this relationship that 1 over R equivalent is equal to 1 over R1 plus 1 over R2. And this is how equivalent resistors are calculated, or the equivalent resistance is calculated for a parallel circuit. Now, here there was, when I look at my original picture, there's only 2 resistors. If I had another one in there, maybe an R3 there, we would just have a plus 1 over R3 over on the right and so forth. I'm not going to go through and work that out, but all right, so that's how you calculate the resistance of a parallel combination. I'm going to go ahead and pause this for a moment, clean it up, and draw a series circuit. Okay, I'm back, and what I've done here is clean my picture up a little bit. I've drawn a new circuit. This is called a series circuit. I've got a pair of resistors. I've got a battery source of voltage, and again, the idea is I want to be able to know, how do we find a single resistance value that we can put in place of this pair and have these two pictures be equivalent, right? And that's what the equivalent resistance is. And just like the previous problem, I'm going to go ahead and color code potentials. This is all one potential to there. Now, the kicker, though, is that there is going to be a drop in potential across R1. So now we have a new potential, which is the same. It's good from here to here. Then there's another drop in potential. Right? This would all now be one potential. It's all one color black. I'm just going to leave it. So it's important to know here that we do have 3 different potentials in the picture on the left. Right? Picture on the right, this red potential is good right to here. In this picture, that would be good to there and no further. If I just kind of work it around, right, this is black to this side of R2, that would be to here in this picture. Right. Now, this only has one loop, so it's important to notice there's only one current in this picture. Oops, so I'll draw that in black. Right, and that current would be this way, and that's the one I would say, I'll just call it I, or I think before I called it current coming from the battery, but this will be good enough for now. We only have one current. That current would be here in this picture. And in this example, it's not the currents that add up to something. We're going to talk about the voltages now. If I take the voltage between black and blue, I'm going to call that voltage across resistor 2. And I look right here, blue to red, I'm going to call that voltage on resistor 1. That gets me from, that gets me basically to the other side of the battery. So the voltage of the battery is equal to the voltage across R1 plus the voltage across R2. So I can write this relationship out. V is equal to V1 plus V2. Right? And just like I did before, since V equals IR, here we can write, whoops, let me back that up here. IR equivalent. Now, here's where I'm getting that from. This voltage is the voltage across this, which is equal to the voltage across this. Right? So IR equivalent is equal to the voltage across resistor 1. That's going to be IR1 plus the voltage across resistor 2, which is going to be IR2. And it's important to note that these I's are all the same, right? When we looked at the parallel combination, it was the voltages which were the same. Well, the voltages are not the same here. Red to blue, blue to black. But the current is the same. There's only one single loop here. If I take a current measurement anywhere in this circuit, I'm going to get the current I'm calling I. So the current is the same, and it therefore divides out. And what we have is that R equivalent is just the sum of R1 plus R2. And here I only had one resistor. Had I put more resistors in, the same thing would have happened. If I put a third resistor in here, I'd have a third resistor here. And if I put a fourth resistor, I'd have a fourth resistor, and so forth. So, simply put, equivalent resistance, how it's calculated, depends on whether the series is, or the circuit you're looking at is a series circuit or a parallel circuit. For circuits in series, the equivalent resistance is the sum of all the resistors. So it's going to be equal R1 plus R2 plus no matter how many of them they are. If the series is a parallel circuit, and this is what the parallels look like, and perhaps more, then the equivalent resistance is found like this. 1 over equivalent resistance equals 1 over R1 plus 1 over R2 plus etc. And then you put in the values for R1, R2, R3, etc., and just calculate the equivalent resistances as needed. So, the purpose of this video is just to demonstrate a little bit about how equivalent resistance is calculated. I'll have more videos where I go over them and use them in examples. I do want to point out that not all circuits are divided into series and parallel. Usually big complex circuits, pieces of it are in series, pieces of it are in parallel, but there are also pieces that just cannot be simplified, and those you have to handle in a different way, and I'll cover those when I get to them. So anyway, hope you enjoyed this. I think I'll write up some examples. Have a great day.